Well, it's 12:02, so maybe I'll go ahead and get things started here. First of all, good afternoon, everybody. Welcome to the Climate Change Institute lecture series. I've been given the privilege of introducing our speaker today, Robert Ackert. I've been lucky enough to know Robert Ackert for about 16 years. I met Robert when I was a graduate student here at UMaine, a master's student, and I went to this place behind me, the Ohio Range in Antarctica, on a project that Robert was PI on. So I was in the field with Robert in 2004, and Hal Barnes was also a PI on that project. But Robert's been connected to the University of Maine for quite some time. He received his bachelor degree here in 1979. He was a master's student here working in Antarctica with George Denton, and he received his master's degree in, when was it? 1990, right, Robert? And
Something like that, yep.
yeah, and then he did his PhD at Woods Hole, working with Mark Kurz, also on exposure dating techniques to resolve chronologies of glaciation in Antarctica. So Robert's done a tremendous amount of field work. He's spent, I think, 17 seasons in Antarctica. He's worked in southern Patagonia. He's even written papers on rock glaciers in the western United States. And if I remember correctly, you also may have done some work in Sweden as well at some point. Anyway, it's a delight to have Robert back virtually to speak with us at the University of Maine. Robert is applying to be an affiliate here at Maine. It sounds like he's going to be spending more time in the area. And so this talk is related to his building that connection with the Institute. So with that said, thank you very much, Robert. This is great. I can't wait to hear what you've been up to. So please take it away.
Okay. It's a real pleasure to be here. I guess what I'll do is just flip over to screen sharing now, if I can figure that out again. Oh, there it is. Okay. Okay, so does everybody see that okay? I'm going to be talking to you today about trying to constrain what the ice sheet looked like during interglacial conditions. And I'm going to be talking about things that go back almost 20 years. I have a long list of collaborators here. These ones on the left, you'll see, are all people involved with the University of Maine. And on the top of the list is Hal Barnes. I'm really sad that Hal can't be here today, but he was really, the start of all of this work that I'm going to talk to you about today. So a fundamental question for Antarctic research, maybe one of the biggest ones, is what is the ice sheet going to do as the climate warms? And this has been the focus for research for over 40 years. I don't know if it tallied up all of the money that ODT has spent on this project. There's probably this one question is probably hundreds of millions of dollars between glacial geology and glaciology over the years. And of course, we're in the situation where we wonder if this situation we see here, where much of the West Antarctic ice sheet collapses and sea level rises, is a possibility for our future, either in the near term or long term. So what we've done is, myself and a whole myriad of other people, is to try to put constraints on what the ice sheet has looked like in the past. And we focus most on what the ice sheet has looked like when it was bigger than it is, because that's what you can do. That's what's exposed on the flanks of mountains in Antarctica. but really what we really want to know is what it looked like when it was smaller, and that's hard to do because everything is covered by the present ice sheet. So the Antarctic ice sheet is kind of unique among ice sheets in that it still exists, so we can look at the present ice dynamics, and mountains, excuse me, protrude through the ice surface, which act like dipsticks, which let us gauge the thickness in the interior, in addition to having control on the periphery of the ice sheet. So it was Hal Barnes that first thought this up when he proposed to do this approach at Mount Weishi and later in the Asgard range. These sites that I have pointed out here are in the interior of the West Antarctic ice sheet, near the dome of the ice sheet or the divide. And so they provide important constraints on the ice volume and thickness of the ice sheet. So how do we go about doing this is, it turns out that most of the bedrock in the interior of Antarctica is very highly weathered and has probably millions of years of exposure. And if you landed at some place like the Ohio Range and started climbing up one of these nude attacks, you'd come across a series of deposits and erosional features that let you gauge how high the ice sheet was. So you'll go from perched erratics and then places where you can see the bedrock has been quarried away. I should just back up and say that, you know, in the interior, all the ice is cold base. So you don't have the typical tills and striations and things that you find in Maine, for example. But the cold base ice can move off blocks which have detached from previous weathering, and even snap off delicate weathering features. I coined the term vandalized bedrock because as you go up, you'll see this cavernously weathered granite. And it really looks like some person just walked up there with a rock hammer, just randomly knocking, you know, these delicate things off, and you'll see like fresh surfaces. And then eventually you get to a place where there's no more erratics, and all of the delicate features, very delicate features, are preserved, and that's where we assume that there's a trim line. And so doing this, and myself and, you know, again, many other people, some of them in the audience here, have got a pretty good idea of what the Antarctic ice sheet has been doing since the last glacial maximum. But, you know, if we want to figure out what it was doing when it was smaller, we have to look under the ice sheet. And this is still as far as I know, the limit of the evidence for that. It came, you know, over 20 years ago, where they found diatoms and excess beryllium-10 in a core through what was upstream B, or now I believe Williams ice sheet. This is actually one of the odder plots I've ever come across. You can see we have diatoms on one axis plotted against beryllium concentration on the other, but I think the point was to show that there's sort of a mixing relationship. So another way to do this is to actually bore into bedrock under the ice sheet and look for cosmogenic nuclides that are produced when the rock was exposed to cosmogenic radiation. So I have a little cartoon here, and the idea is you could go to the ice edge, then march along and drill holes and sample the bedrock. And you would expect, as you go down deeper, you would have, assuming that the ice sheet has in fact been lower than present, the cosmogenic nuclide concentrations would decrease. At a point, you come to some point where, as John Stone says, you'll find bedrock that was only exposed once, and then get to a point presumably where the ice has always covered it. And then you'd have some idea about where this past ice level was. And we can use a whole bevy of cosmogenic nuclides, stable nuclides, neon-21, helium-3, and then the familiar beryllium-10, aluminum-26. And an exciting new thing is that we can use carbon-14, insta to produce carbon-14. So, so in this talk, I'm going to basically talk about two places, the Ohio Range and Mount Weishi. So first going into the Ohio Range, which is located here at the end of the Transact Mountains, sort of one of the last kind of outcrops before it disappears completely beneath the ice sheet. And if you get there, it looks something like this. And in this field season that Aaron alluded to back in the early 2000s, we mapped this upper trim line and found it was about 125 meters above the present ice elevation. And we came up with actually only two exposure ranges that were clearly not with prior exposure, and they came in to be about 10 or 12,000 years. And in contrast, the underlying bedrock is cavernously weathered and millions of years old. I also point out, so here is the Bennick nuditax that are sticking through this blue ice area in the lee of the mountain range, where we'll look in more detail. So if you get down close to those nuditax, they look like this. You can see the bedrock is granite and quite weathered, and they stick not too far out of the ice sheet and below this trim lines. These were completely covered during the last high stand about 10,000 years ago, and probably many times before that. So we measured neon-21 and beryllium-10 in samples from the peaks of those nuditax. And just for people that are not that thinking about cosmogenic nuclides all the time, I'll explain this diagram. You can see we have neon concentration on the x-axis, and because that's a stable nuclide, you can imagine that this is pretty much analogous to time. And then on the y-axis, we have the ratio of the beryllium-10 to neon-21, and they are normalized by their production rate. So when you first start to irradiate a sample at the surface, the ratio will be 1. As time goes on, some of the beryllium-10 starts to decay, so the ratio of these two isotopes goes down. And this upper line here is what you would get over time for a sample that has no erosion. So the ratio slowly goes down from 1 with time. And then this lower line here is what we call a steady state line. So in a process that's kind of analogous to secular equilibrium with radioactive decay series, the concentration of radioactive cosmogenic nuclide will eventually saturate or become constant as the decay is equal to the production. And if you take erosion into account, even a stable nuclide like neon-21 will also reach secular equilibrium, but it takes a lot longer than beryllium-10. So it's very useful for looking at these really old surfaces. And this line is actually a locus of points of the steady state where the sample would follow some trajectory through this field and end here. And that'll become a little bit more clear in this next picture. So here's some example of our samples and some modeled trajectories. And this area between the curves is referred to as a simple exposure field, because you can get there with simple exposure. But you can hide a lot of cover in this area, in fact. And these trajectories are based on the Paladin-Ducano ice sheet model of the last 5 million years. You probably can't see the axis here, but this is 5 million years. This is the surface history. And so you can actually just go along here for any elevation at your grid point and see if the model predicts the rock to be exposed or unexposed, and then model how the cosmogenic nuclides increase with time. And it turns out you can actually get to our data points using reasonable exposure histories and erosion rates for the most part, for the first two, where there's, and can note the exposure ages are millions of years, 4 million years here, 3 million years, with quite reasonable erosion rates, typical for Antarctica. But the lowest peak is not reached by this model, which suggests that the ice is seeing too much cover, and the ice surface, the modeled ice surface, is on average too high. We can get there by kind of artificially lowering the ice surface in the model, which again is just consistent with the idea that the model doesn't seem to be too far off. Of course, this doesn't prove the model is correct. It just shows that the model is reasonable, and kind of gives you some encouragement to forge ahead. So another thing you can do with that model is, oops. Oh, here we go, sorry. See what the projected concentrations are at the base of the Nude attack and even farther down under the ice. And you'll see that now the model predicts that you will be in this field below the steady state line, which is clear evidence of cover. And this is basically what we use to argue to go back to the Ohio Range and do some drilling, because we had a clear opportunity to test this model and to look for empirical evidence that the ice sheet was lower. So that's what we did. And this is data from Seth Campbell, who was with us at the time, of course. So we did, or Seth did really, you know, a massive job of surveying, and we located places where we would drill to come back the following season. So you can see this, there's a nice, this is actually the ridge following off of this Nude attack here that kind of cuts across these surface tracks. And then if you look, just another example of this really beautiful GPR data. So we have our ridge coming down, and the idea is we're going to drill into this bedrock surface here to get our samples. And that's what they did. Unfortunately, I wasn't on this field season because I had a climbing accident and was in a wheelchair for a few months, but the rest of the team did a great job. We covered quite a bit of core. This was the first application of using this Winky drill to do shallow drilling and get samples from under the present ice sheet. And so we got up to 28 meters below the surface, which was not bad for a first application. The hope is that this drill can eventually go up to, well, they said they would get us 80 meters at the Mount Weishi, so we'll see. And just to see where we are here, we have that same transect across this larger Bennett Nude attack, and then one more core from this smaller Nude attack nearby, which was very useful to have two different sites to look at and give you some confidence in your result. Because you can imagine, you know, if you've collected exposure dates, you know that you spend a lot of time carefully selecting your sample so that, you know, you think it's telling you, answering the question you're trying to ask. So, for example, you know, this is just what the bedrock looks next to that transect. And you can imagine if you were just blindly sampling, you know, we could hit into this rubble pile or whatnot. So the strategy was to look for where the bedrock was fairly steep, so a situation that might look like this, and be more confident that we're just hitting direct bedrock. We also had a unique kind of opportunity here to actually see what the bedrock looked like under the ice sheet. And this was Seth Campbell's brilliant idea to actually go down in a crevasse that forms in the lee of this smaller nunatak and see what we can see. Our mountaineer was not pleased with this idea. I think her idea was that her job was to keep us out of crevasses, and if Seth was not there with his great experience and expertise, she never would have allowed it. But as it is, we went down, and I believe about 18 or 20 meters down below the ice surface, we found weathered bedrock. This is our grad student, Jenny Middleton, going down to sample it. So we really know what it looks. You can see the frozen bed ice is just, adhering to the rock. One of the cores they pulled up actually had the ice rock interface preserved. So this is really the meat of the project right here. So this is the data from the cores. Each one of these points is a sample from the cores. These are the depths. So this one's 12, 26, and 28 meters below the surface. And the first takeaway is that these core profiles follow what we call a spallation profile, which is what you would expect for samples that have been irradiated at the surface. There's a small contribution due to muons, and muons penetrate much deeper into the rock than neutrons, which are what causing the spallation. So bedrock that's more than 2 meters deep, there's essentially no spallation produced cosmogenic nuclides, but muons are produced at very low levels, but measurable hundreds of meters into the rock. So you could have cosmogenic nuclides in bedrock that was always been buried by the ice sheet, that's never seen the light of day. But if you drill the core of that, it would have a profile that looks more like this for the muons. So this is clear evidence of subaerial exposure of this bedrock in the past, which is consistent with the fact that we think it was highly weathered based on what we could see not too much above these levels. So this is these data, I should say, this is the first cosmogenic nuclide data from below the Antarctic ice sheet. There is samples from Greenland, but this is the first from Antarctica. So this was a success in itself for this first attempt. So to look at a little bit more detail, this is that same kind of graph that I showed before, except now we're looking at aluminum 26 versus beryllium 10. They're normalized, so it starts at 1, and we have the same field of simple exposure, 0 erosion, steady state. And you can see that 2 of the samples fall well within the field that has experienced significant cover. Actually 3, there's another one over here. And interestingly, the shallowest sample doesn't show any evidence of cover at all, and not very much erosion either. That may be due to the production rate, which we have to normalize for the shielding correction. So we don't really know what the shielding of these samples were. The production rate might be off slightly, or this might just be real. It might be that 12 meters down is almost always exposed. And I recently reviewed a paper by, oh, my name, that had quite a few dates from Antarctica, and there were some samples, in fact, that fell right on the line like this. So I don't think we can discount it as necessarily wrong, but we won't think about that, discuss that one too much further. So one way to look at these samples is to follow what we call just a two-stage exposure history, where the sample was exposed for a certain amount of time and then covered. And if you do that, you can plot on this same diagram lines of constant exposure and kinds of constant burial, because as things are burial, they move downward in this line. And given that we're basically shooting blind to take these samples, I find it really encouraging that they're actually they show quite a consistent, similar history between them. So the way I would interpret it, you can see that this is, I believe, the 200,000 years of burial line. And they all lie within area about the same area, and the interpretation would be that the sample started off with different exposure. There was history or subaerial exposure, probably due to quarrying and peeling off of large blocks of the nunatak. But over the last several 100,000 years, they've seen almost identical exposure histories, and you can see that they are all at the same depth. This is 28, 26, 25, and again, this is from a separate nunatak about 1 kilometer away, which is pretty conclusive. So one thing, so this is not exactly what we expected from our model, but where we were thinking that exposure was only happening during extreme interglacial events. In reality, these sites are exposed about half the time, which means that they must be exposed during the glacial periods as well during interglacial periods, and that the ice level at present may in fact be anomalously high. Why that? Oops. Oops. It's going back here. So this is just again to review what the Paladin DeCanto, the most recent version they have, would have projected for these sites. So the fact that it is the trajectory falls to the right of these samples suggests that the model is still showing too much ice cover at these sites, which is consistent with what we had before. And just to show you what we're doing here, this is an example of the surface elevation history, and at the site or within the nearest grid site. And basically, you can pick your present elevation and whether the site is above or below ice, and calculate your model here. And what we're seeing is some elevation relative to this this elevation history, which would have to fall something like this, so that you're getting significant exposure and cover at about equal percentages. But this is quite a bit higher elevation than we are actually at the Ohio range, which would actually be, closer to 15. Well, you can see the present elevation on the axis there. It's at about 1540. So just to recap that section, so bedrock about 20 meters, 8 meters below the ice has been exposed. The ice elevations have been lower than present, roughly half the time over the last sort of 400,000 years. And that lower interior waste levels are not restricted to interglacials. And bedrock below 28 meters was mostly exposed probably during the Pliocene, consistent with the Pollard and DeCanto predictions. So all in all, I think this was a pretty successful enterprise for a first time out. But of course, this doesn't directly address the question that I posed at the beginning, which was, what was the ice sheet like during the last interglacial? So I'm now going to move to Mount Weishi, where that is answering that question, I think is very possible. So just to review, here we are now in Marie Birdland, and Hal started this off in 1995 there. So this is what Mount Weishi looks like from satellite imagery. For some reason, if you go into Google Earth, there's really great imagery of Mount Weishi in comparison to a lot of other places on the ice sheet. I don't know who at Google just became infatuated with this or what, but anyway, it's really nice to be able to just go into Google Earth and be able to fly around the field area. So Mount Weishi is a volcano of Plio-Pleistocene age. There are rocks as old as a couple million years up in the caldera. There's a large blue ice ablation area immediately to the south of it, which means that moraines can form on the flank of the volcano, which is mostly ice-free, as you can see here. And there are numerous parasitic cones that are erupted on the flank. You can see many of them here. We've counted up actually about 20 of them. And for cosmogenic nuclides, the flows are have an ideal composition with olivine, clinopyroxene, and plagioclase, with olivine and clinopyroxene being ideal for helium-3 measurements, which is, I have to admit, my favorite nuclide. So this is just a map from that first field season. What we found was there's this moraine band on the flank of the volcano. There's a debris band on the ice. And there are previously been mapped extensive maps of these tephra layers, which in fact you can see here from space coming into the blue ice area. So you actually get an idea for how this ice is flowing in. These are actually massive locally derived tephra with actual volcanic bombs in it. Some of these other ones are far derived ashes from Mount Berlin and Mount Moulton. So these tephra layers have been mapped in detail. Some of them have been dated. We've got some new dates pending on those, and some by correlation by Nelia Dunbar. So the for real old news, the helium exposure ranges of the moraine bands up to 40 meters above the present ice are about 10K, the same as we found in the Ohio range. And in fact, this early Holocene high stand is found throughout interior Antarctica. Again, way back then, Jim Fastook, I didn't know if he was here talking, watching, but he had one of the early models that showed this high stand, which agreed with our dating, both in the timing and the elevation. So there's actually quite a few older ages from above 40 meters. This curve at the bottom is a PDF, just to show you the distribution. Here is the peak at 10,000, but there's some other ones from the LGM. And then there's a big batch of ages between 40 and 100,000. And there seems to be some correlation with the projected ice levels and temperature from the Dome Fuji ice core. And again, this is the elevation from the Paladin de Canto model. So there seems to be some correlation with peaks and exposure ages with relatively warm periods. And we'll come back to why that may be near the end here. So Mount Weishi is an ideal site to try to constrain downdraw during the last interglacial using cosmogenic nuclides in bedrock cores. And that's mostly because the bedrock is very young. So we don't have the problem that we had in the Ohio range where there's millions of years exposure and you're not going to see in beryllium 10 or aluminum 26 any sort of noticeable change just from one recent exposure of a few thousand years. So during 2018 and 19, we did field work back at Mount Weishi, and I was real excited to actually get there because I processed these samples that Hal had collected, but I had never been there. So I always had a little bit of nervousness about the interpretations I made, having not been in the field. And so in addition, what we did was, again, we did site evaluation. Seth did the GPR, and the team from New Mexico Tech collected samples and mapped the lava flows for 4039. So we had a really successful season. We had about 28 perfect days on the field site. They literally mapped every outcrop on the southern flank of the volcano. This is actually just a simplified map, and collected samples for dating from every flow. One of the takeaways is that all of the flows are subaerial. So there was never a higher ice level than present that interacted with an actual eruption and caused ice lava interaction. This picture with Nelia is a classic haloclastite with pillow basalts, which is evidence of lava ice interaction. But this is not in situ. It's a gigantic block in the moraine, and we never saw anything like that in situ. So that puts limits on ice extent at Mount Weishi going back hundreds of thousands of years, never higher than present, or higher than the moraines, I should say. And we had some really exciting data has come out from the lab at New Mexico Tech that show that Mount Weishi was actually active during the last interglacial. So we have 3 lava flows mapped. They're younger than 125,000 years. So if those lava flows extend under the ice sheet, and you can see that it looks like, in fact, they do, this one probably passes under the moraine and into the ice sheet. If you drill into those and you find any cosmogenic nuclides, there's no question that this is from ice lowering during the last interglacial. And if the lavas show no interaction with ice, then you know they were subaerial. So we have kind of independent line of evidence for lower than present ice levels, even absent cosmogenic nuclide data. Hopefully we'll have both, and we can actually put a limit on how long that exposure was before it was covered up again. So we actually have another batch of data that's come in that I didn't incorporate here, but you can see, just for reference, the uncertainty on these ages. The group at New Mexico Tech specializes in 4039 dating of mafic, young mafic rocks, which is hard because of their low potassium content. And you can see that the youngest age here has got about a 10% uncertainty, but there's a pretty low uncertainty on this of just 3% or something on this older age, which is pretty good. Interestingly, they had a lot of other dates on that were older flows, and there seems to be a correlation with the with warm periods, which suggests that there is some linkage between the ice elevation and eruptions at Mount Weishi. This has been kind of a linkage, which basically involves unloading the magma chambers during deglaciation, is well documented in Iceland, but hasn't definitively been shown in Antarctica before. So this was pretty exciting and suggests that, you know, just the presence of these lava flows may be a proxy for lower ice levels and previous interglacials. This is the GPI data that we did for the site location. Again, Seth exceeded himself even again with unbelievably 1,000 kilometers of data. He spent most of the field season riding on a snowmobile, measuring up to 1,200 meters and large kilometer grids, so we have an idea of the larger ice flow. And you know, also detailed like 10-meter grids that we walked out to map potential sites for drilling next season. And one exciting thing, an additional exciting thing about that data was that there's good evidence for unconformities within the ice, which we suspect were formed when the ice was lower. So here's a really clear one here. And then you can see the deformation of the overlying layers. You have to imagine this was taken on a slope. This was probably a straight line that followed the snowbank down along the flank of the mountain. And then as the ice level came up, with mostly vertical in these blue ice zones, there's very little horizontal motion. So mostly uplift of the layers and warping them. So let me see. Yeah, okay. So we'll come back to what we can do with that potentially in our future work here. So I also have done some new surface exposure dating, and the most important aspect of that was to actually look at this ice cord moraine, which Hal didn't even sample because he and I assumed that this was a very young feature, which is typical if you find basically a debris band on the existing ice sheet. But in fact, it appears to be tens of thousands of years old and have roughly the same age distribution as the moraine band that's stranded on the flank of the mountain itself. So that's going to give us some better ideas on how these moraines form. So that basically sums it up. We're going to go back there hopefully next year and collect those drill core samples. Things in the works are measured chlorine-36 and carbon-14, the Ohio range. Eager grant with Seth Campbell to try to put dates on these unconformities, which will really complement any history we get out of the subglacial bedrock. And both of these places are ideal for going back with the ASICS drill, which can go back hundreds of meters down and potentially get into those rocks, which in fact have never been exposed, and put some constraints on how far the ice goes down during collapse events. So I think I'll leave it there and look forward to some questions.
Great, thank you very much, Robert. Does anyone have questions for Robert?
I have a quick question, Robert. What is a volcanic bomb?
Oh, that's like a blob of lava that gets shot out of the volcano, and they can be any size, but that just means that you're very close to the volcano, as corresponding to these very fine tephras that can travel hundreds or even thousands of kilometers from the volcano.
Thank you.
It's Jim Fastook here.
Oh, there he is.
I was a little late at the beginning, but this is great, Bob. I'm very, very impressed by the thoroughness of the attack on this problem. It's a real tribute to Hal that he came up with this idea way, way, way back, and I'm really happy to see you extending it further into the ice to get the low stand. That's really innovative, and it looks like a really hard problem, but you seem to have a really good handle on it. So I'm very encouraged by this.
Yeah, and I meant to point out in the Paulo and DeCanto model agreed completely with your work from 20 years earlier. So that's a really robust conclusion, I think, about that early Holocene high stand.
Yeah, the hardest thing about paleo modeling is making up the climate that you use for the past. And all of the models use some kind of simple parameterization based on, tying it to an ocean core or an ice core. And so that's the hard part of modeling, is making up the climate. And so these ice elevations are very sensitive to what you decide the accumulation rate is during the past. And that's always going to be uncertain because we have no measurements of climate in the past. We can only make approximations. But it is great to see that their much more sophisticated model agrees with the old-fashioned humism. So thank you.
Yeah.
It's Andrei Korbatov, Rob. Can I ask you a question about volcano tectonics? I understand the general constraints here, but what's the latest thinking, like how the volcano that's potentially very unstable tectonically, because you have a magma coming, magma leaving, elevation changes. What's the latest thinking, how it could really work as a like an indicator of elevation for the ice? I really...
Oh, okay. Well, again, these volcanoes in the interior of Antarctica are pretty stable because the erosion rates are so low. So that you can actually see a kind of break in the morphology. I think it's about 8 or 9 million years ago, where volcanoes older than that are all chewed up, just like you would expect in temperate climates. And then volcanoes younger than that are still pretty pristine. So they seem to be able to hold up under these polar climate conditions. But there is a question about, the one interesting, certainly if you have ice lowering of hundreds of meters during a collapse event, it's possible that the flanks of the volcano, especially if they've been building up in equilibrium with higher ice levels, could be subject to some, massive sort of slope failure. And in fact, there is quite a scarp along the flank of the volcano that we are still puzzling on how that formed. And it may actually be that during one of these earlier well, it truncates lava flows that are 350,000 years old. So there may have been like a massive kind of landslide locally on one side of the mountain there, but I think they basically stay there just like a granite mountain sticking through the ice.
Thank you. Yeah, sounds great. Thank you.
More questions for Robert? Well, I have one, Robert. In relation to what Andre just asked, I was looking at the timing of the Argon ages on your lava flows, and you noted that they correspond to previous interglacials. Do you think that has anything to do with what Charlie Langmuir and Peter Hybers have been suggesting about the ability of the ice load to kind of squelch volcanism?
Yeah, exactly. So that's sort of they were looking more at the mid-ocean ridges, which would be sort of out of phase with this, right? Because they're being squelched by higher ocean levels. But in Iceland, about between 12 and 13,000 years ago, as the ice cap melted there, there was a huge pulse of volcanism, which was attributed to lowering the pressure on these magma systems. And most of the classic table mountains, or tuyas, I guess, were formed within just a few thousand years due to that. So there's empirical evidence, and in Iceland, they've done some theoretical analysis that shows how this could work. I mean, this is another whole nother field that we're thinking about, but certainly we've started talking about whether we could get a lot of seismometers on Mount Weishi and start to try to image the magma chamber to understand this problem better.
Thank you. Any other questions for Robert?
I have one. Hi, Robert.
Hi.
I was wondering, just thinking back to your Ohio range data for a moment, you mentioned that it appears that the ice level is higher now than it normally would be, and that it spends a lot of time, not only during interglacial periods, but during glacial periods lower than present. Why do you think it is relatively high now? Is it just a matter of time, not enough time yet since deglaciation, or is there some other reason?
I think that it's a combination of the accumulation rate and the and the temperature. So for interglacials where there isn't a collapse event, this might be the normal, which might only be a few thousand years out of a 100,000 year cycle. So I guess that would be the first thing. And then and a caveat that I didn't mention is that we're assuming that these blue ice areas go up and down in synchrony with the larger ice sheet around them. And to first order, that I think is true. But in these blue ice areas where they're basically a balance of upwelling ice from compression and sublimation. So I think during glacial periods, that balance may be shifted. You can imagine that maybe sublimation rates, well, accumulation rates are lower, sublimation rates might be lower also because it's colder, but it also depends on wind and a lot of other things. So I think making assumptions that those things haven't changed in small detail is probably not a good idea.
Thank you.
Time for another question or two for Robert. Well, if not, then
Okay, well,
Yeah.
either people are totally confused or it was clear enough. So that's good. I'll assume the latter.
well, no, I thought it was very clear. Thank you very much. That was a fantastic presentation. Really great to see all the work you've been doing, Robert. So hope to get to see you in person here sometime soon when we get this pandemic in the rear view mirror.
Yeah, I'm looking forward to that to myself. And yeah, it seems like, maybe next summer if we all have the vaccine or something, but at least can make an appearance with a mask anyway.
Sounds good.
Okay, well, again, it was a real pleasure to speak to this community. Like I said, it's kind of coming full circle for my strong roots at the University of Maine. I look forward to working with folks again up there. Yeah, I do. One other thing I want to mention is that the beryllium and aluminum data that I presented was actually done. The chemical separations were actually done at the University of Maine. So that was with Zach, right? So and also Aaron. So I have to thank them again for that, and look forward to potentially using those excellent facilities in the future.
It would be a pleasure. Absolutely. Well, thank you very much, Robert, and thank you everyone for coming. And with that said, see you next time.
All right. Well, I'll try to check in on some of these talks in the future in the Bournes symposium there.
Thanks, Robert. Good to see you.
Yep. Bye.
We'll talk to you soon.